Okay, well, welcome back. Let's see, a few questions were asked about the project. So turn in the whole Sparse 3 folder, and then if the uf-get directory is really huge, remove it, and then submit it without that. It's easier for us to have the whole Sparse 3 zip or tar file, because if you've got modifications, you've got maybe modified the include file or the source directory or whatever. You know, so you could in theory just send us the edits, but then we have to recreate what you had, and sometimes you might miss something. And believe me, I've done this before. So just tar up or zip up the whole thing, and it should be about a megabyte or two, so it's not that big a deal. And you know, if it's 5 megabytes because you've got a bunch of matrices in there and you forgot to remove them, that's no big deal either. So either way is fine. And that's due Friday. I'll be around all day today. The Nuri, the TA, will be. He's got a conflict on Friday at 2:30, so he's going to move his office hours, I think, to noon to 2. But I'll be around Friday as well. So if you've got last-minute questions about the project, I'll be around, and I'll be around tomorrow as well. So everything should be all set, you know, for you to do the stuff. Okay. I want to pick up. I mean, with chapter 2. Probably can't quite finish chapter 2 today, but might get close. And that's on matrix addition. And it may seem odd, you know, why am I looking at matrix multiplication before I do addition? Isn't addition more basic? Well, yes, it is, but actually I do it the other way around, because there's matrix addition written as a matrix multiplication, right? I mean, think about this. If I want to compute C equals alpha A plus beta B, where alpha and beta are scalars, and the only reason I put that in there because it's easy to do. And if you want to, it's easy to do, so you might as well provide that option. If you don't want it, it's just to do A plus B, just set alpha and beta to 1. It's easy to do because as you're bringing in the data, it's very easy to multiply by a scalar, and that's commonly, like if you want to subtract two matrices, right? You can just do A minus B. Of course, remember, 3 minus 3 is non-zero, so subtraction doesn't delete any zeros. If you want to delete zeros from your matrix, you have to explicitly do this computation on C, then you drop the zeros from C explicitly. Personally, I wish that's the way MATLAB did it, but you know, it doesn't. So anyway, you can, if you write this as a block matrix, a 1 by 2 block matrix, and then alpha I and beta times I, then if you do the block matrix multiplication, you know, just put your finger down, pretend these are scalars, right? Just like, then you get this. So we don't need a matrix addition if we have matrix multiplication. Now, of course, this, if I were just to call the multiply code as is, I'd have to create this matrix, A concatenated with B, which is not that hard to do, but I mean, that's more memory. I don't want to do that. And I would also have to create this funny matrix with the triplet, with the, you know, this alpha on the diagonal and beta on the diagonal. So I'm not actually going to create these matrices, but the code is going to mimic this. So it's going to, and it's going to use those scatter-gather functions that I saw before. So the multiply, let's go back a little bit. So here's the multiply. You're going to see that pretty much everything up to this point is going to be the same, except now A and Z plus B and Z is actually going to be accurate. Because it's going to be an upper bound, right? On the addition of A plus B, the upper bound on the non-zeros in C is the non-zeros in A plus the non-zeros in B. You can't get any more than that. So that's kind of handy because that means I can throw this away. All right. And now think about what's happening here. Here I'm cycling through the B matrix. Well, now iterating through all the entries in the column of the B matrix. Well, now this B matrix is this piece right here, which there's always two entries. Yeah, Spencer.
In your code here, you have the W equals CS calc M size of int.
Right.
When I tried to do something like that in my code for the assignment, I got a seg fault.
You did? Well,
yeah.
did you use CSI for C-Sparse 3?
I just changed it to 8 and it works.
Ugh. You put 8?
Yeah.
Oh, that's bad.
I don't know what it's supposed to be. But
it shouldn't be size of int. Okay, in the C-Sparse.
I had like that, but it wasn't working.
It should not be int. It should be size of CSI.
Okay, does that work?
It should, yeah.
I didn't know if that like method only worked with like primitives or like I don't know.
No, it should say size of CSI.
Okay, I'll try that. That was my
If you
question.
put in size of int, it'll break. You have a 64-bit computer? Yeah, it'll break.
Yeah, it was
Because it's too small.
Yeah, it just closed the program.
Yeah. That's, yeah. Right. The most common result of a seg fault in your MEX functions is MATLAB just disappears.
I got both.
Yeah. Or you'll get some gross, ugly, useless, blah. Yeah, stack dump, as if that's useful. Okay. And then MATLAB asks, do you want to continue? I don't think so. Sometimes you want to continue a little bit just to see where you were. But MATLAB, the MathWorks says, look, don't. In fact, I had a discussion with the MathWorks. It's like, why do you want to continue?
To save your stuff.
Well, no, not to save your stuff, because your stuff, if you've mangled your pointers, you don't want to save anything. Yeah. Or you could, but any bets are off. No, the only reason you want to continue is potentially to see where you were when you died. Any extra little bit of debugging information you can glean from your current state before you terminate MATLAB is good. But yeah, in C-Sparse 3, the integer is replaced with CSI. So use size of CSI. So if you look at C-Sparse 3 right here, it'll say size of CSI.
Okay, I can get it.
Anyway, so what's going to have to happen here is we're going to have to cycle through both the A and the B matrix. Okay. Because this is going through, I'm sorry, no. It's going to cycle through, no it's not. It's going to cycle through all the columns of C. But right here, it's going to have to iterate through both alpha and beta. And alpha gets multiplied by the A matrix, and beta will multiply the column of B. So here we have the entry in B multiplying with the column of A. But you're going to see both A and B used here, but then you're going to see the alpha and the beta used here. And that's it. That's the add. So, and there'll be none of this doubling, no dynamic table needed. So as a result then, the code looks very, very similar. So here's the addition. Whoops, that's the scatter. It's going to be used the same. And this is why I made this a separate function, because the scatter is going to be the same. There's the addition right here. So if you line up the matrix addition and the matrix multiply and do a diff between them, you'll see they're almost identical up to, all this is the same here to here. It's identical, okay? And then here, there's the alpha, there's the beta with A and with B, and there's the gather. That's it. There's the addition. So there's no... so if you understand the matrix multiply, you understand the addition. So if you think about what's happening here from scratch, if you don't want to think about it in terms of matrix multiply, all that's happening is column by column, we just have to take the column of A and the column of B and add them together. All right. And so to do that, we scatter the one into our workspace. We scatter the second one into the workspace. Keep track of where the new entries are. That's what the scatter function is doing. So it's doing the set union, remember, and then storing the result with the gather. So it's a set union operation of the two vectors, one vector at a time. So that's the matrix addition. Any questions about that? Hopefully that's fairly straightforward.
Slightly related. Are we gonna go down memory management? If we obviously have a memory leak, if we don't close everything off at the end, is that?
Oh, your code should have memory leaks. I would encourage you to make sure your code does not have memory leaks.
Okay.
Okay. Can you get an A in this course with memory leaks? Yeah.
Okay.
All right. Part of me wants to say no, because I don't know. I mean, I'm weird. I like to do the theory. I like to do the algorithms, but I like to write code, and I don't like to write just mere research prototype code that no one's ever going to use. I want to have an impact with my work, and I like to take it all the way to production quality code. In fact, better than production quality code. So I'm weird.
Yeah,
I think I must have an obsessive complex or something like that. Yeah. In fact, there's some very careful design done for memory management here. For instance, what happens? See, you're allocating 2 objects. Okay. Now think about that. If you allocate, or 3 actually, 1, 2, 3. You're allocating 3 objects. If at this point this could fail. Okay, and then if so, what do you do? Well, you've allocated nothing so far. You could return at this point. That would add some extra code here. I handle that condition. But think about what's happening here. Suppose this one succeeds, but the second one fails. So what do you just return at that point? No, you have to return and free the one that did succeed. Otherwise, you have a leak. So there's all these kinds of extra conditions you have to worry about. So what I do here is I just allocate all 3, okay? But you notice before I use, see here, this would cause a seg fault. If C fails, this causes a seg fault. So I allocate all 3 objects, here, here, and here. And before I actually use them, then I'm going to check all 3 of them. I'm going to check, is C exist, does W exist, and if I need it, does X exist? So if I'm adding just 2 binary patterns, the values don't exist, and I don't need this. If any of these are true, that is if C is null or W is null, or if I need the values and X is null, then I return on failure. And this 0 says I failed. And I passed this return CS done. CS done returns a null pointer to a sparse matrix, a CS star type. And CS done takes 3 input arguments. It takes this return value of the sparse matrix, and it takes in 2 workspaces of type double. And what it does on 0 is it frees all 3 and returns null, which is what you want to do. Of course, if W is already null, it doesn't free it. You don't want to free a null pointer. On the other hand, if I succeed down here, that means do free W and X because they're workspace. They have to be, but don't free C, but return it as the return value CS done, and it gets returned here. So it's a one-line error handle. It's a one-line wrap-up function, basically, one-liner that on return on error here and return on success here, and they do slightly different things depending on. Both of them free the workspace, but one of them frees the sparse matrix you've just created, because it's certainly possible here for X to fail but C to succeed, which seems a little odd. But actually that's possible, because what if M is enormous and A and Z and B and Z are tiny? Then it's quite possible for C to succeed but W or X to fail. So yeah, I'm very persnickety about memory failures and error handling and testing. In fact, I don't know if this is. I hope this doesn't sound like I'm bragging. It just is. Please don't get me wrong when I say the following statement. But NASA did a study where they used extreme techniques, software engineering-wise, to develop software to put up in space. Nothing to do with my code. And they got a bug rate of, I believe, 0.1 per 1,000 lines of code. Okay, but they said this is infeasible for any, and this is satellite software. Okay, then they said this is infeasible for a real project, but we got 0.1. Well, I've counted up the bugs in my code over the years that have been put into MATLAB, and my bug rate is 3 times less than that. So I have a bit of an advantage, okay, because, well, I guess I'm a bit obsessive. I don't know. Maybe that goes with my dyslexia. I don't know. But my advantage is that I'm dealing with pure linear algebraic functions. Okay. So I may do a matrix multiply, I may do a matrix factorization, and so forth. It's very complicated to do those things, but at the end of the day, I'm trying to solve a linear system. Does AX equals B? I have a very simple check to see, did I get the right answer? Okay, so when I'm hammering my code, if there's one small error in the code, it's going to give me the wrong answer, most likely, not always. And so because of that, the way I do the testing, it's very easy to catch errors. It's hard to write the code, but it's easy to test. But see, most code is not like that. Most code is both hard to write. Well, maybe this kind of code is actually harder to write. Other code is probably easier to write, but then harder to test. And so you're going to get a higher bug rate. I mean, how do you test a GUI this way? What do you know? What's the right output of a GUI? Well, the mouse moves here. Well, how do you got to look at it? Think about that. Testing a GUI is tedious work. So I don't have that problem. So that's kind of an advantage an explanation why I can get such a low bug rate. Anyway, so that's matrix addition. So the next thing we want to look at to do with matrices is basic functions is to permute them. Okay, and this comes up in several contexts. Let's see. I don't actually. Yeah. This is a smaller picture of a larger piece of the puzzle, but permutation comes up because oftentimes you want to say do a factorization of not the original matrix because that causes too much fill-in, but you want to permute the matrix you want to make it numerically stable. So when you're doing Gaussian elimination, you don't want to divide by 0, right? If you have this matrix and you want to solve that linear system, you can't divide by 0. That's not good. But if you swap the first two rows, I guess there's only two rows, or the two columns, then you'll get a better answer. You get an unanswer instead of no answer at all. So permutation is important for numerical purposes, but it's also important for sparsity. And here's where we get our NP-hard problem. Okay, so if I have a matrix that looks like this, it's sort of an arrowhead shape. The first row is non-zero, and the first column is non-zero, and then there's non-zeros on the diagonal. Now think about that linear system as a system of equations. Would you do Gaussian elimination with the following? Would you take the first equation, solve for the first unknown, and plug it into all of these? That would be insane. You'd have n-1 equations that all are all non-zeros. All the variables are in every equation. That's ridiculous. You'd start instead at the opposite. You'd take, let's say, the last equation, solve for x sub n, and remove it from the one equation up here in which it appears, which is the top one. And you do constant work. So if you do it in this direction, the factorization is order n time. If you do it in this direction, the factorization is order n cubed, which is an enormous difference. And the memory is n squared. And here the memory is order n. So you'd really like to do this and not that. I mean, this can be infeasible for a large problem, and this can be trivial. This could take every supercomputer on the planet to solve, and this I could do on my laptop, depending on the value of n for the same matrix. So we need to permute the matrix. But there's other reasons to permute matrices. Part of it is if you want to take in MATLAB, you can write this. This is one way of writing this permutation. You can specify P and Q as permutation vectors. Okay, so if this is a 3 by 3 matrix, and I ask for it's in MATLAB A, if I say A 1:3, 2:3, for instance, okay, then what I'm asking for are the first 3 rows and the first 2 columns. So I'm getting a submatrix. It's very commonly done in MATLAB. You want to get a submatrix, or maybe you want to get a scalar. Okay, but you don't have to ask for it in this order. You could say, well, oh, don't give me 1, 2, 1, 2, 3. Give me 3, 1, 2 as a vector, which says, oh, first give me the third row, and then give me the first one, and then the second one. So on the output, it's going to look like this row is going to come first, and then these two rows are going to come next. So you've extracted a submatrix, and you've done a permutation. So this kind of stuff happens all the time in matrices. You want to grab a piece of it, you want to swap things around, and so it's like a permutation. Now the codes here don't do the submatrix stuff. I don't have a code in Sparse for extracting out a submatrix, which I think I leave that as an exercise to the reader. I think if you guys want a challenging, yeah, it's problem 2.24. If you want a challenging project, that's kind of fun. Actually, 2.25 is even harder. That's the opposite, where you take a matrix. Doing this in MATLAB is not easy. Think about that. Okay, where I and j is either a scalar or it's a submatrix, perhaps permuted. That's not an easy thing to do. If you think about the data structure, you have to modify this matrix A. It's non-trivial. And I don't have code for that in here. That's left as an exercise. So permutation. The first thing then to see is that most of the time permutation, well, many times, permutations are handled with vectors and not matrices. So think about this 3, 1, 2. That's a permutation vector that says, hey, I want the third thing first, and then I want the first thing and then the second thing. That can be represented as a vector, 3, 1, 2, or it can be represented as a row matrix. So I can do P times A. So I can do the following. I could say, well, give me A 3, 1, 2, colon. So I'm not doing anything to the columns at the moment, but I want to do something to the rows. Doing something to the rows, I can do the same with a permutation matrix to the left. Left always operates on rows. To the right always operates on columns. To see that, I guess what you can do is do the following. What you need to look at is say, well, let's take A and split it into its rows, all right? And then notice that if this is an identity, if this is a row of an identity matrix, so in particular, if I want 3 first, I'm going to choose 0, 0, 1. This is like a choice vector that says, hey, give me the third thing. So now do the block matrix multiply. Multiply this times this, and the result at the top is A3. All right, and now I want A1, so I'm going to choose this. This times this gives me A1. And then 0, 1, 0, this times this gives me A2. So this permutation matrix to the left does the same as this row permutation vector, 3, 1, 2. So now how do we go from the 3, 1, 2 to this matrix? This, of course, is a very nice sparse matrix. We could store this with the sparse matrix with order n on zeros very efficiently. And in fact, it's a bit of a toss-up as to which is faster. I didn't write this code in MATLAB, but I did write this one, the matrix multiplication in MATLAB. And I have in there, because since I know that permutation matrices are so important, I actually have a special check to say, oh, this is a permutation matrix. I can do this a lot faster than a regular matrix. And so I do that check, and well, it handles matrices that are slightly more elaborate than permutation. But permutation matrices, there's a special test in there that says, in the matrix multiplication, that says, hey, one of these matrices is a permutation, so things can be done more efficiently. So how do you go from the 3, 1, 2 to that matrix and back again? It's this right here. So if we want to, this one here, for instance, if I have this lower, what I do is I use lowercase p and q for permutation vectors and uppercase p and q for permutation matrices. And what's interesting about, as an aside about writing a book, is you collect all your knowledge about a topic, or at least the important stuff, and put it down on paper, and then you can forget it and come back to it. It's like, well, now what was that again? And you actually read my own book sometimes because I forget. And not too much of it, but I forget these 4 rows is probably in the book is the most frequently thing I look up because I can never remember which goes in which direction. I either have to work it out from scratch or I just look it up. So it's this third line of on this slide I want to focus on here. I've got A, P, comma, colon written on the chalk there, and P times A. All right. Now, when I have a permutation matrix and a permutation vector that do the same thing. So what I want to do here then is I need to specify. You see, this was a 3, but that gave the column index in which that entry needs to appear. So it's row 1, column 3. See, there's the 3. See, I need to go from the 3, 1, 2 to this matrix. So there's the 3, there's the 1, and there's the 2. But those specify the columns of that permutation matrix. And the rows are 1, 2, 3. So if I create a triplet matrix that says 1, 2, 3 for the row indices, and for the column indices 3, 1, 2, which now that's the same as P, and the binary value is 1, 1, 1, then that'll create my permutation matrix. So that's what you see here. And the sparse function in MATLAB, if you've not played with it much yet, you don't have to actually specify a vector of values here. You can specify a scalar, and that scalar gets expanded into a vector of the proper size effectively. It doesn't actually get expanded, but conceptually it expands into a vector of all ones inside the sparse function. Now, so that's the third line. Now going back does this, and there's an odd little thing of a P transpose here. Think about if I were to do a find on this function, okay, on this matrix, okay. Let's see. Then I'm not going to get this back again. Because that is a set of triplets, but it's not in column major order. It's not ordered by columns. So what's going to be stored internally is column 1, 2. It's going to be first sorted, if you will, by column. 1, 2, 3. So if 1 goes with 2, and column 2 has the entry 3 in it, and there. So in the PI, and this is, of course, there's no PJ, but it's going to be column 1, column 2, and column 3. So that's the sparse matrix P. So the 3, 1, 2 is gone. If I do then a find on P, I get 2, 3, 1 and 1, 2, 3, and it doesn't help me any. So that's not any good if I leave out the transpose. If, on the other hand, if I take this P matrix and transpose it, okay, then you get a matrix that looks like, let's see if I can do the transpose, 0, 0, 1, 1, 0, 0, 0, 1, 0. Essentially what happens when you do the transpose is you put it in row-oriented form. You sort by row, not by column. That's another way of thinking about it. And if I sort by row, I get back to this over here. So that's one way of thinking about it is P transpose converts a compressed column matrix into a compressed row matrix, and that's what you want here to extract out the permutation vector 3, 1, 2 as now the column indices, which is what you gave it in the first place over here. So that's why these go back and forth between each other. This takes the vector P to the matrix P. This takes the matrix P to the vector P, and vice versa. Now, the column permutation is a little simpler. Okay, if I have A times Q, and there are times when you want to do both, or one or the other. And the reason you want to permute columns of a sparse matrix, at least when you just want to solve a linear system, is again for fill-reducing orderings. You don't want to do Gaussian elimination with the existing columns in that order. You want to reorder the columns to reduce fill-in, and say to A times Q. And or to make it more numerically stable, whatever. There's various reasons. And suppose I want to do this. Have a permutation that jumbles up the columns this way. Then let me write out, and really, I guess, to be persnickety, I should have put transposes here to denote row indices, row vectors, but whatever, I didn't do that. I just called this as row 1, row 2, and row 3. Now I'm going to call A1 column 1. All right, I'm just reusing names for different things. So there's my block matrix as a collection of columns. All right, now what I want to do is ask, what do I need to do to get, what kind of matrix do I need to put here to get out the matrix A3, A1, A2 as my new matrix? That's A times Q, the permuted. See, 3, 1, 2 is my permutation vector I'm playing with. Well, if you put your finger down, you're going to go across the row here and across the column here. And so if I want to choose, if this is a vector of choice here that you're making the choice of, 0, 0, 1 is what you need. So if I put a 0 here, and a 1 here, then I'm going to choose the third item, right? And now if I want to choose the first item, I need 1, 0, 0 here. So now you get that. This times this gives you this. Do you see how useful the block matrix multiply is used for? I mean, it's not just, you're going to see it over and over again, multiplying two block matrices together. Here you see it being used to explain why permutation works. Okay, you're going to see it for how triangular solves work, and how you saw it earlier how matrix multiply worked and matrix addition, and all the factorization methods. You'll see it again and again and again. So please make sure you understand how this works when you do matrix multiplication with block matrices. That's all I'm doing. So 1, 0, 0 and 0, 1, 0. So if I put my finger down here, I get A2, which is what I want. So this is my permutation matrix Q. If this is my vector lowercase q, this is Q the matrix. Q the vector, Q the matrix. And so what kind of matrix would this be? Well, if I list out all the entries, this is row 1, column 3. This is, no it's not. It's row, see, I got my rows and columns mixed up. You can guarantee I'm going to do that again. This is row 3, column 1. This is row 1, column 2, and this is row 2, column 3. No, that's too funny. I said 2 and I wrote 3. That's a first. I do that when my brain is on the 3, my hand is on the 2. Okay, there. Those are my 3 entries in my permutation matrix Q, and you immediately see the 3, 1, 2 here are the row indices. So Q, if I want to create capital Q from lowercase q, there's my row indices, and there's 1, 2, 3. So there's creating Q from big Q from little q. And the other direction, okay, if I do a find, well, I just did the find here. The find always produces the result in column major order, right? Because the compressed sparse column major, you're writing a find function, right? The most natural way is to leave the row indices in place and just tack on the column values. Well, the columns are sorted. Column 1, column 2, and column 3. And the row indices are 3, 1, 2, and there's your Q vector. So back and forth then between a column permutation and a column vector. So it's they're slightly different, right, between the two. I mean, I can take, if I have this vector of 3, 1, 2, I'll call it T. T equals 3, 1, 2. Then I can use it as a row permutation vector like this, or I can use it as a column permutation vector like that, indistinguishably. But if I convert this thing into a matrix, if I convert it this way, then I only have a row permutation vector, P times A, or capital, whoops, I call it T. T times A, and A times T will be very different. A times T will not give me this matrix, A3, A1, A2. It'll give me something altogether different. So it'll give me the inverse permutation. And it's an inverse because, in fact, with permutation matrices are orthogonal in the sense that any orthogonal matrix, its transpose is its own inverse. So if A, here's a bit of linear algebra, is orthogonal, then A inverse equals A transpose. Unfortunately, I used the letter T here. I shouldn't have done that. I'll call it Z instead, I guess. Okay, if I want to permute A, the columns, in the same manner that I permute A, the rows, I need Z transpose here. Which I haven't shown up here, but okay, so that's how matrix permutations happen. And what I have inside the code is I always represent the permutations inside C-sparse as vectors. Of course, I can always convert them to matrices using the compress function if I want. But one thing that is important to be able to do is to invert a permutation vector. And here, let me explain why that's important. And this is going to be very important later on in the course. As you're dealing with permutation vectors, there's many ways of thinking about permutation vectors. I've shown them how you can think about them in terms of matrix multiplication. But there's another way of looking at permutation vectors, and this is going from I call it from old to new and from new to old. It's a mapping. Because if I have P times A, okay, then, and unfortunately I erased here, I've got it here. The old row 1 is now the new row 2. So think of it as a space. You have a space of old rows and a space of new rows, a space of old indices and a space of new. And there's going to be cases you're going to need to convert. Well, which one here refers to which one here? And back again, if I have a new row and it's new 2, which old row does that correspond with? Oh, that's the old row 1. So I like to think of it in terms of old and new because old is maybe the original matrix A and new is the matrix you've permuted. Okay? And you can think of the permutation as a function that maps between old and new, and then the inverse permutation is an inverse of that function, goes back again from new to old. And so what is this thing right here, P? Well, if P is the vector 3, 1, 2, then I can write that P of 1 equals 3, P of 2 equals 1, P of 3 equals 2. So what do these three things represent? Well, these three things represent the fact that P of new, I want to make sure, yeah, is old. That is, here, the new 1 is the old 3. So here's the new row 1, it's the old 3. The new 2 is the old 1. And that's what I've written down here. The old 1 and the new is the new 2. And the new 3 is the old 2. The new row 3, here's the new row 3. The new third row is the old second row before I permuted it. So now think about this. P is just a vector, and it could be used to implement a function, right? The lookup vector makes a nice way of thinking of it as a function. But this function, P, says, well, I can give it new, and I get out old. Great. But what if I need the opposite? What if I need the inverse of this function? Say, call it P inverse. In that case, I want to take the old and give back the new. Why would I want that? Well, what if I'm permuting a matrix? Maybe I'm permuting it implicitly. Think about that. You're walking through, and this is a really, really important thing to be able to do. You're walking through a matrix. You're wanting to manipulate it. But in fact, you're actually wanting to manipulate the matrix in its permuted form, a permuted row indices. But maybe let's leave the columns alone. So I want to visit the matrix. I want to visit all the entries in the matrix. But as I visit it, I want to translate it to a permuted matrix. How would I do that? Well, again, forget the column permutations. Let's just think about the rows. So I'll go down a row, and I'll see, oh, there's a row 2. But you see, what is that? That's an old row 2. So if I have a function that takes that number 2 and converts it to the new row index, then that would be the inverse permutation vector, from old back to new again. Okay? So if I had the following vector, I'll call it P_inv. And let's see, this would be, the inverse would be P_inv of 1 is 2, P_inv of 2 is 3, and P_inverse of 3 is 1. So there's my inverse permutation lookup table, if you will. That's this inverse. So P_inverse of 1 is 2. So this is old, and this is new. And so what I'm meaning here is that P_inverse of old is new. It's the opposite of this here. Of this. We have these two functions. One function and one its inverse. So I call this thing an inverse permutation vector, and I call this thing the permutation vector. And they're related to each other. One's the inverse of the other. And if I have the inverse permutation, that's rather handy, because what that means is this the Pennsylvania matrix, right? Okay, P times A. I can construct on the fly. Suppose I have an algorithm that wants to operate on P times A. What do I do? Well, I could permute it first and then work on it. But instead what I could do is I could walk through the columns. Every time I see a row index, I could say, oh, no. That's the old row index. I don't want that one. I want the new one. So every time you see a row index, you just put it through this mapping and you're done. You don't have to create a new matrix. All you got to do, and I like to think of it as looking at through a lens. I've got this A matrix here, and I want to leave it alone, but I want to take my glasses off and like twist them around and say, oh yeah, that's P times A. All right, and the lens is my permutation vector, inverse permutation vector. And then sometimes you need to go the opposite direction. You may have new row indices that you want to map back to the old, and so you have to use this vector. You have to put in the new and get out the old. So again, it's another lens. So there's a need then for a permutation vector and potentially its inverse. And so here's a pair of functions which goes back and forth between the two. CSPVec and CSIPVec. PVec constructs, well, what it does, this doesn't actually compute the, it doesn't compute the inverse. I'm sorry, I spoke too soon here. What this function does, what these two functions do is both of these functions construct a permuted vector x. So I may need to, what they do here is they're going to apply a permutation to a vector, a double precision vector, not to a matrix, but to a vector. So what I'm doing then is p times x to get the output. What do I call it? Oh, p times b, I'm sorry. P times b, I don't want to get x. Well, so there's two things that can happen here. One is I may want to permute the vector, and here I want to apply the inverse. I may have the inverse permutation, but I still want to produce p times x. So both of these compute p times x, but one is going to use the permutation vector, the other is going to use the inverse permutation vector. And you can use both because they're dense vectors. You can do an easy lookup. And with the pvec, what happens is I'm iterating through k, where k is the new. Remember, the permutation vector is stored in the form p of new equals old. And so this is the new k, and old is p of k. What that means is if x is in the new, I want to index x with k. So you see over there x of k. But you see over here b of p of k. And that's what the function then does. It goes through all the new indices k, and it just assigns b of p of k to x of k. Except that you notice this funny ternary operator here. What the heck is that doing? Well, I have... identity permutations are so important, and they come up so frequently, that if I want to say, well, okay, here's a function, it can handle a permuted matrix, and it takes as input a matrix, and it takes as input a permutation. Well, what if I don't want to use that feature? I want to say, look, I don't want to deal with a permuted matrix. I want to just do it on the original matrix. You could construct a permutation vector of that's identity. 1, 2, 3. Well, sorry, it's all zero-based notation, right? I start with 0 now. 0 through n minus 1, and build the thing, and then pass it in, and then the lookup table would be p of k is, oh, I got k. Oh, surprise, surprise. Okay, so you have to build that vector of length n, and that's a pain. And so what I have is a convention that if the vector is null, then that represents the identity vector. So if p is null, that means this becomes just a vector copy. B of k is assigned to x of k. Over here, this is doing p times b, but it's using the inverse permutation vector instead. So here it's walking through, then I have to go through, I still want to say x of new equals b of old. Okay. But now with the inverse permutation vector, I have to give it the old index and get out the new. So that means it has to look like the following. I have to write x of p of k equals b of k. So that's what this loop does. X of p of k equals b of k. So these two functions apply a permutation to a vector, whether it's been given as a permutation vector or whether you have the permutation represented as its inverse. Both of these compute p times b, if you will. They do a permutation on that vector. So that's vector permutation. And the next thing, which is on the next slide, is going back and forth between the two. Okay? And I've got just a few seconds left, so I'll have to leave this for next class. But basically, if you've got a permutation vector, but you want its inverse, how do you compute it? And that's what this does. So take a look at this, and I'll pick it up next class. See you then.